and I will take my time as requested. Okay, so last week we concluded with our shortest walk component. That just draws your most suitable pathway from point A down here to point B over here. Again, you'll find your own points, but this is following that most suitable pathway that's within, I believe this one is set to a 4% slope or less. So anything that exceeds 4% gets kind of filtered out so that it's only relying on this kind of, oops, I guess it's really this network of curves. So this is the entire network of paths that you could follow. This little operation here just filters it down to being only paths that are 4% or less. So that's where we concluded last week. Now we want to give it some color range because even though they all these segments fit within that 4% or less slope, they still have different slope percentages for each section or each segment. So it's going to be important just to kind of show that graphically as well so that it's understood that there's still going to be some areas that are more strenuous than others perhaps. So what we're going to do is we're going to take this is creating a polyline curve, as you can see when I hover over that W. That's the path itself. But then there's also a couple other components, such as the indices. So again, this is a pathway that's made up of that entire network of curves. This gives essentially all those index items for each one of those curves that's being used right here. So we're really just going to work or focus on those two elements. So what we're going to do is take this curve and fracture it into all those segments again. So again, this is where we're deconstructing it. So utility, explode, it'll just go ahead and explode it all into all those different segments. So what we want to do now is figure out the slope percentage of each one of those segments. We don't have to figure out that operation again. We really already have that information back over here. So here's out of our slope component, the slope values out of this negative component. So what we want to do is use this same component here, which filters it out, to do it for those values as well. So I'm going to go to sets, list, dispatch. And just to iterate again, what this does is that this component creates a pattern of whether an object fulfills that criteria or not. In this case, it's looking at all the slope values of that entire network and saying which ones are 4% or smaller and those that are greater. And it's giving you that true or false logic. So true if it's 4% or less, or false if it's greater than 4%. So it could be 4.00001%. And it's technically greater. It might actually round it down, but either way. So that's what's giving our kind of true or false logic. The dispatch component is basically building off of that pattern, this bottom one, the p-value. You can see dispatch pattern, it's looking for that true or false pattern. So that's what we're going to plug into here, the same thing we did before. And then it's looking at, okay, what objects are you actually looking at in relation to that data? So this is like a true and false pattern of data. And this is the objects itself that you're trying to correlate with that. So in this case, we're looking at those slope percentages. So I'm going to drag this one into here. And again, I'm going to use whatever we dragged out of that first one, so out of the A output, we're going to do the same thing for this. We're going to use the A output. So we're going to go ahead and hide that. And so, like I said, we're we have the index items or indices for all these segments. Now we're going to use that to figure out all those values themselves. So I go to list item. So again, it's looking for an object, in this case, the slope percentages. And then it's going to use the indices from here to figure out the actual value. So what you should have coming out of this explode component is the same value or the same amount out of this. So this case, I have 34 line curves. I'm not saying that you should have that many, but whatever that number is should be the same as here. You'll see there's also 36 slope percentage values. So this is where we start to give it the color gradient. We do the same thing that we've done before for mapping out those colors. We go to math, domain, bounds to see what our high and our low values are. So we have sloping almost 10% in the downward direction and 3.1% in the upward direction. We'll go ahead and deconstruct those domains. And this is where we want to, again, be careful with what we choose. I'll go back to parameters, input, use our color gradient. I'll set this default to maybe this one again. So green means it's nice and easy versus the red is starting to go in the upward direction. So in this case, we want that start, so the negative value to go into here. So if it's essentially a nice kind of downward direction, the up in here. This is all of our slope percentages, so that goes into here. And now we have our color association for all these curves. I can go to display, preview, custom preview. So take that geometry, drag into there. And so you'll see that right now it's given a lot of red. So in this case, because -9 degrees, I mean, you're technically, even if it's in the downward direction, you're going to have to come back that way. So if you actually crisscross these, you can see that this is a little more accurate. So here you can see that this is where they are fairly slow, and it's only over here where it does climb fairly quickly that it gets that red gradient. So you're most likely going to have to kind of do the opposite for these. So have those crisscross. So there you go. Now you have your color values for your pathway. So now we want to create those section cuts along the pathway. So turn this off. So we're going to take that same shortest walkway, so this one, and we're going to find planes along it based off of a certain distance. So let's go ahead and do curve, division, divide by a distance. I'm going to take this curve, so again, that shortest walk P-line curve, determine a distance. I'm going to do every 50 feet. I think your assignment asks for 100 feet, so I'm just going to do this because I can. And again, you can see, like, if you want to go for that A, you might want to do more section cuts to show a little more variety. So right now you can see now I have points every 50 feet. I'll stay in the curve tab here, go to analysis, and choose perpendicular frame. So this is going to create our frame every 50 feet. So I will again plug my curve into that frame. We're looking to create that frame along this curve, that shortest walk curve again. And you can see it's looking for a lowercase t. That's why we use this component so that we also get this t value or the parameters. I'm not going to go into too much detail into it, but this is just gives you a more kind of precise data sorting, so to speak. So now you can see there's these frames that are going along this pathway every 50 feet. And this is why we use the frames, because essentially what we're going to do is contour our surface at each one of these frames. So I'll go to intersect, or physical, I think, or is it somewhere? Contour. So instead of using the contour that we've done before, there's also an option to contour along designated planes on a surface. So in this case, the perpendicular frames that we just created. So I'm going to choose this one. It says contour EX, not the standard contour component. So the first thing it's asking for is the shape to contour. You should, starting back over here, we created a Delaney mesh. And that's the same thing that we're going to use as our surface to contour. So I'm going to drag that Delaney mesh over into my contour. So that goes into the shape component or input. And here you'll see it's asking for a plane. We just created frames, which are essentially the same thing. Like I've said before in the past, the nomenclature, the terms might be slightly different, but if the icons match, that's really what's important. So you can see this is called frames, but you can see the icon over here is this kind of slightly skewed rectangle. And the same thing is shown over here. It's technically a plane that it's asking for, but again, it's looking for that skewed rectangle. So it's the same thing. So I'm going to drag that into here. This will take a second. So now instead of like the standard contour component where we choose like, okay, draw a contour every so feet, this one's going to only draw a contour wherever those planes are. Oops, and there's one more thing we have to do. Instead of leaving it blank, we want to also say, give this a 0 value. That's because it's trying to look for other information, but if you set it to 0, it'll just focus on those planes. So now you can see that it cuts a contour line at each one of those planes across the entire model, which is exactly what we're looking for. We just don't need to do it for that entire stretch. We only need 60 or so feet total, so 30 feet in each direction. So that way they can get shortened. So that's what we're going to do with this next procedure, is start to fracture out these contours. So we're going to go back over to curve, do division, and tell it to shatter at a certain point. So we're going to take our contour lines, and this is where we want to shatter them. And then it also needs a parameter. It essentially needs to know where are we going to shatter it. We basically want it to happen at the same intersection points as our planes. So you'll see that not only does this divide distance create that t value for our frames, but it also creates that same t value that we can input into here. So I'm going to, you can see this creates a dashed line. So essentially each one of those contour lines are on their own data tree branch. So we need to do the same thing for this. So this is why we're going to graft it. We're going to You can see this has a solid line, meaning all that data is in the same pool, whereas we need each one of those points to be on its own branch, just like over here. So I'm going to right click, say graphed, so that up arrow, drag that into there. And now these are actually going to be fractured. It doesn't appear so, but you can see in the list here that, I don't know why that one doesn't, but for the most part, it's showing that there's two numbers for each one of these, meaning it's been fractured at that point in both directions, or essentially dissected or bisected in this case. So now we can start to single out the contour lines in each direction. So I'm going to go to sets, list item. I guess I could also explode this. Let's do it that way. I'm going to go to tree and say explode tree. I'll drag this into here, and this is basically going to say, oops. Nope, we don't want this one, sorry. Yeah, we're gonna stick with this list item component. So I'm gonna drag this into here. I'm gonna copy and paste another one and give this an index item of 1. Because the way this works is that because there's 2 items for each one of those contours, for the most part, again, I don't know why it has that one, but there's 2 polyline curves at each one of those intersection points. And you can see over on the left that there's an index value of 0 for all of them, and also an index value of 1. This is what these items do, is that it says, okay, this one, it's just defaults to 0, so that's why I didn't put anything in there. So this is going to separate all of these 0 polylines, and this one's separating all the polylines with a 1. So that's really what it's doing, is separating those 2 fragments. So now you can see when I select here, this is, let's also turn off. Oops, that's weird. That's not correct. Maybe I can, instead of graphing it, maybe I need to flatten it. No, that's, I don't know why that's happening. Let's double check this. I don't know why that's. Oh, we forgot to do one more thing for this. That's what I thought I was missing. Sorry for that. So we need to find the point on these curves first. So I'm going to go to curve and choose curve closest point. So it's going to look for these points. So that's what I was saying. So like this divide distance creates that point over there, which is here. And then it's also looking for the curve itself. So we're going to also believe we use our contour lines for this one. Yeah. So we're looking for that point closest to these contours that we just created our along our surface. And then this is also, this again, we're going to go ahead and graft these. So now we have them all where they should be. This goes into our T value. So my apologies for that part. Let's just shift those over a little and turn this off. So now you can see that they're nice and dissected, where these ones are all kind of on the right-hand side of that curve. Here's the ones all on the left-hand side. This is where we start to kind of shrink them. All right, so what we need to do now is determine how far over do we want these curves to go. I'll show you one thing. We're going to backtrack a little, but it's for the purpose of, again, some clarity. So let's go ahead and divide these curves. So divide by a distance again. Do each one of them, let's say, every 10 feet. Okay, so we can turn this off, or let's keep those on. So like I said, we're gonna go back a little bit, but we are first going to, again, we're gonna use this kind of list item logic to figure out which point that we're going to stop it at. So if I do sets list item, do it for here and here, essentially, let's do a number slider 1 to 5. The way this is going to work is that it's going to choose the point that's 10 feet away from the path. So you can see, because I've divided it every 10 feet, the first point, or the list item 1, is going to find that point that's 10 feet away. If I drag it over 2, then that finds the 20-foot point. If I keep dragging 30 feet, 40 feet, so forth and so on. So it's essentially like taking these contours that are following the path, dividing them into segments that are 10 feet apart, and then it's trying to figure out, okay, do you want to choose the one that's 10 feet away, 20 feet, 30? So you can see how they all kind of move away. The thing, though, is that if I select here, you'll see that I don't see any of these points highlighting near that curve. And the reason for that is because you can kind of see that over here it's 10 feet away from that way, meaning most likely the first point in the other direction is actually all the way over here, because it's cut the pathway. Let's just say, here's our contour that it's made, there's the pathway. We've split it at that point, right? We've then divided it every 10 feet. So each one of those bisected curves or contours is divided into 10-foot segments. But the way this logic is working is that we might assume that it's counting out every 10 feet from the point, where in fact, it's actually reading 10 feet from here, and then still 10 feet from there. So we have to actually reverse that data. What the heck is that? Ah, awesome. So what we're going to do is actually reverse the curve for this one. So I'm going to go back up to curve, utilities, flip curve, drag that into here. And now you should see that when I have both of these highlighted near the pathway, now you can see that they're right there 10 feet away. And if I drag it, they both start to move out away. So now they are following this logic where they're spreading out from that dissection point, or keep saying dissection or bisection. So I'm going to drag it out to be about 30 feet away from the path in each direction. So it's going to be a total of a 60-foot wide profile. In this case, this just kind of gives you a visual representation, but the way we're going to, again, trim away this curve is that we're going to use the parameters to do so. So again, we're going to shatter this curve at those parameters. So again, I'm going to take my shattered curve, so in this case, the flipped one. I'm going to drag this into here instead and shatter it there. And do the same thing over here. So I'm going to replace it. So I'm actually looking for that item. Drag this into there. I think that's how I want to do it. Let's just double check. Yep, that seems right. Yep, okay. So we've shattered them at those parameters. Oops, wrong one. No. Yes. Now I've lost track. Okay, so there's the curve. We're shattering at that parameter. Good. We're doing that one for this one as well. So that way they have their own groups together. So the list item into that shatter, they're all using that same indices of 3. And now we're going to once again, use that list item to say, the way this is going to work is that it's been shattered again. These contours have been shattered into 2 segments once again. So now it's being cut at 30 feet. So each one of these gets cut at 30 feet. But there's still technically 2 segments. Because we're just essentially moving in the outward direction, the first list item is going to be the segment we want. So I'm going to do list item, drag that into there, drag this into there, can turn all this junk off. Oops, there's still something highlighted. Oops. Uh-oh. It's because I used the right one. So there's that one. What the heck? Let's double check one last time. That is odd. Because is it this one that's all screwy? Yeah, which I'm feeling has to do with when I reverse this. I'm trying to. Oh, I think that's why. 1 second. So it actually needs to go like this. So it's still that item. Oh, geez. So make sure to flip those. So we still single it out, but then we flip its direction. Because we were actually like flipping both, which made it a bit of a pain in the ass. So turn this back on. There we go. So going back here, it's same list item, but then it's after you separate it with that list item that you flip it. And that's what goes into everything. So apologies. But now you can see it's nice and clean. So we're all good. So let's go ahead and join these curves together because now we can see that there's still segments going off from those points. So curve, join curves. We can flatten this, so we don't really need them to be separate. Now we can see that we've gone from the 28 segments, we've joined them, so it should be cut in half, and there you go. Now we have 14 curves. Oops, let's turn that off. So final part, we're going to project these curves down for the base of our profile and connect them. So let's go ahead and project to a plane. So project object onto a plane. We need to make sure that our plane is in fact below those contours. So you can see that my surface is pretty much right there at the 0. So we want to give them some height. So we can go ahead and create a point. Set that z value to like negative 30 less than 15, negative 15 less than 0. Now they should all be nice and below the actual contours. What we're going to do now is essentially connect these two curves. So we'll find for each of these curves the endpoints and start points for both of them. So there's the start and end points of the existing contours or the section contours, and the start and end for the ones that we projected down. And essentially all you have to do is connect the S from this one to this one and the E to the E. So the endpoints for both of them and the start points using a line from 2 points. So primitive line, you can see it's asking for 2 points. So let's plug the S into the A and this S into the B, paste, copy and paste it, and do the E into the A over here and the E into the B here. Now you can see that they're actually nice and solid. We'll turn these points off. And because we don't want to deal with sections or segments, we want to actually join all 4 of those segments together. So we'll go to Utility, Join Curves, and we're just going to plug them all into here. So hold Shift to join them all. And now you'll see you have 4 polyline curves, and voila. And what's good, again, like having it all parametric, is that you can make these contours. Maybe you want to have them every 25 feet or so. And start to see how easy it is to make them denser. You can decide to go out, we'll say just every 10 feet, but then instead of 30 feet, you can do them to be shorter. They could be longer. All of it's going to respond nicely to your existing pathway. Easy as pie. So I'm going to go ahead and stop recording so it's not too long.